Okay, so in this third video, I'm going to talk about energy with respect to capacitors and then something called dielectrics. Okay, so let's start with energy. So just like capacitors can be used to store charge, they can also be used to store energy. So we're going to talk about the relationship between charge, stored, and energy. So if we store a total charge of Q on a capacitor with a capacitance of C, then you can calculate the total energy stored by that capacitor just with this relationship here. Okay, where Q is charge and C is capacitance. Okay, and U, as we've seen before, is just the potential electrical energy. Okay, and yeah, Q is charge, and C is capacitance. Okay, so this is sort of like bringing it all together. There are a few different ways of expressing the energy stored on a capacitor. You can actually write it in three different ways, and it's useful to sort of like be familiar with or at least know how to derive the other two. So this is one. Let's call this equation one. The other two are basically just like manipulating, like subbing in relationships that we already know in for the other variables. But depending on like what you have and what you're looking for, it's sometimes useful to express energy using these other two ways. So this is the one that we've already seen, right? With Q and capacitance, right? So the electrical potential energy is just Q squared divided by 2C. If we also know from before that charge is equal to capacitance times the voltage. So we could sub this into that equation, right? And we would get just U equals C squared times delta V squared divided by 2C. That C would cancel with that C, and so we would have C delta V squared divided by 2. So that's sort of like the second way of writing potential energy stored on a capacitor. And then the third way, so like we could I mean, this equation here, I can just rewrite it as capacitance equals charge over voltage, right? So I could sub this into equation one, right? So that would just be, so equation one, remember, is Q squared over 2C. If I sub this in for C, I get Q squared times delta V over 2Q, right? That Q cancels with that Q. And so I get delta V over 2. And so that is sort of like the third equation. Delta V Q, right? Delta V Q over 2, right? Because you only canceled one Q. Okay. So that's good. So that is those are the different ways of expressing the energy of a capacitor. So let's try this sort of example problem. So let's say that we've got 5 identical 400 farad capacitors that are connected in parallel to a 3.4 kilovolt voltage source. I calculate the energy stored in the capacitors, like in total, it's asking. Okay, so we know from the first or the second video that the equivalence capacitor, when you've got capacitors in series, you just add them together, right? So we would have C1 plus C2 plus C3 plus C4 plus C5, right? That would be like how we would calculate the equivalent capacitance of 5 capacitors that are connected in parallel. Okay, so we know that each of them, like C1, ah, Okay. All of the capacitors are the same capacitance. So like C1 equals C2 equals C3 equals C4 equals C5, and each of those equals 400 microfarads. Um, oh, I think there's like this little symbol here is meant to be a micro. Okay, because like if you look at the diagram, it looks like it's a microfarad. Anyway, okay, so we've got 5 times 400 microfarad. Okay, so that's 2,000 is the equivalent capacitance. Okay, and we know that the voltage supplied by the battery is 3.4 kilovolts. And so to calculate the total potential energy on all of those capacitors, we're just going to use the formula 1/2 CV squared because we have both C and V. So that's 1/2 times 2,000 microfarads times 3.4 kilovolts squared, which is going to equal 11.6 kilojoules. Okay, so that would be how much energy that would be stored on all 5 capacitors when they're connected in parallel like that. One sort of like interesting sort of like application, for those of you who are interested in medicine, so an interesting application of capacitors is it is exactly how defibrillators work, right? You've seen, you have to like charge, you've seen like on medical shows, they charge them up to a certain potential difference. Um, and then they discharge them like across, a person's heart as a way of delivering energy to try to sort of like restart the regular like rhythm of the heart rate. Okay, so like a defibrillator is just a giant capacitor. Okay, so here's another example. And this sort of ties together the idea of capacitors in different configurations of circuits and energy. So let's say you have a 9-volt battery and you have 3 identical capacitors, and you've got these 4 different sort of like ways in which the capacitors are connected together. And we want to know which of the following circuits would maximize the total energy stored in all 3 capacitors. Okay, so basically we're looking for the configuration that, like, if we think about what potential energy is, potential in the context of capacitors, potential energy is the capacitance times the voltage squared over 2. And in all 4 cases, the potential difference, this is the same. Okay, because we're told that in all 4 configurations we have a 9-volt battery. Like this is a 9-volt, like all of these, this is a 9-volt. All of these are 9-volt batteries. So the potential in all 4 circuits is the same. So to maximize this, like our job is to maximize the energy. We need to maximize, we want to know like basically which configuration is maximizing capacitance, right? Like we want to maximize capacitance. Okay, so like we're looking for the biggest equivalent capacitance. Okay. So we just sort of have to analyze, and we can kind of do it almost like based on inspection, right? Like if you compare this configuration A. So configuration A, you've got 1, 2, 3, you've got all 3 capacitors in parallel. So the equivalent capacitance is going to be just C plus C plus C, which is 3C. Okay, so that is going to be the largest equivalent capacitance. The smallest equivalent capacitance is going to be this one, right? Where you've got C, 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 and they're all in series. So like if I were to write out the equivalent, let me just do it over here. The equivalent capacitance for configuration C is just going to be like 1 over C plus 1 over C plus 1 over C, which equals 3 over C. So 1 over the equivalence. And so the equivalent capacitance in that situation is just C over 3. So a third of a C. So that this one is going to be, C is going to be like the smallest equivalent capacitance, and A is going to be the largest. Okay, these two here, B and C, they have sort of like a combo deal, right? Like, so to add, and we're going to do this in much more detail next week, but to add up the equivalent capacitance for configuration B and configuration D, you'd have to do it in 2 steps, right? Like you would basically have to like say, okay, these two capacitors, like the equivalent capacitance of just these two is equal to 2C. And then you would sort of redraw the circuit. Like you don't really have to worry about this now. You would redraw the circuit. So this is C, and now this is 2C because I've combined these two here, right? And then I would basically do a second step. I would do 1 over the equivalent capacitance is 1 over C plus 1 over 2C. Okay, and so you would have to find a common denominator and like add it up. And I think it's easy to see that like both the configuration of B and the configuration of D would be somewhere in the middle, right? They're not going to be as small as C, but they're not going to be as big as A. So A is definitely the winner with respect to like the configuration that maximizes the capacitance. And so A is the answer. Okay, I'll erase these so that it's not confusing. Okay, so that's that question. Okay, so that's basically all I wanted to say about energy. It's relatively straightforward. It's really just, understanding the equation and like manipulating it. Okay, so now I want to talk a little bit, the last kind of topic of capacitors is something called dielectrics. So dielectric is an insulating material that is placed between the plates of a capacitor. And what it does is it increases the capacitance. Okay, so remember we said before that you can calculate the capacitance of a capacitor just on the basis of the area of the plates and then the separation between them, sort of the geometry of the configuration. The other sort of like piece of this puzzle is you could also affect the capacitance by whether the capacitor has a dielectric in between the plates or not. Okay, so let me just write this out so you have it. So like what is a dielectric? A dielectric is basically an insulator. It's an insulating material that is placed between the plates of a capacitor. And what does it do? It serves to increases the capacitance. Okay, so let's like write out the mathematical relationship. So if you have a capacitor that doesn't have a dielectric, we often refer to that as just C naught. Okay, so this is like this is referred to as like the capacitance. Um, where the only thing separating the plate is either air or like even a vacuum, right? So it's like basically the capacitance in air, um, or like a vacuum. So i.e., there's like nothing in between the plates, like no dielectric in between the plates. It's just air in between the plates. Okay. I can calculate like the new capacitance of a capacitor by multiplying the capacitance that the capacitor has in like when there's just air separating the plate times something called the dielectric constant, which has this symbol kappa. Okay, so this is the dielectric constant. And it's basically like a factor by which the capacitance increases when you insert the dielectric of that material. So like different types of different materials, like different kinds of insulators have different dielectric constants. Like for example, the dielectric constant of water is about 80, okay, which is pretty high. Okay, the dielectric constant of air is, or like a vacuum, um, like the dielectric constant of air is like basically one. It's like 1.0006. The dielectric constant of a vacuum, like if you sort of like suck out all the air in between the two plates, it's just one. Okay, so these two things are kind of used interchangeably. So when something doesn't have a dielectric, like the kappa is just one, and we don't even really bother to write it into the equation. Okay, it's only if you have something separating the plate that has a substantial kappa, like that it matters. Okay, so let's talk about how the dielectric works. So let's say that you have a parallel plate capacitor where you have positive plate and a negative plate. Okay, and we know from everything that we've learned so far that the electric field is going to be constant and is going to be pointing constant and uniform, and it's going to be pointing from the positive plate to the negative plate. Okay, so I'm just gonna label that with one arrow at the top here. You'll see why in a second. And I'm just gonna call that E naught. Okay, so E naught is the field created by the charged plates. Okay, now I'm going to insert a dielectric. So some sort of insulator. It could be water, right? That has like a very high dielectric constant. The higher the dielectric constant, the more the capacitance of the capacitor will increase from the situation with just air or a vacuum in between the plates. Okay, so let's say that I insert a dielectric in between these two plates. So I'm just going to draw that in as kind of like an orange block. Okay. And this picture down here basically shows you from the molecular level what this would look like. So this box here is the dielectric, and it's showing you like what it would look like when it's not inserted in between the plates. Okay, so this is like an insulating material it's like described here in the absence of an external electric field. Um, and you can see that it's got these sort of like dipoles that are just like not aligned in any way, right? They're kind of like chaotically organized. Like there's no alignment of the molecules within this insulating subject or material. Okay. When I put it in between the two plates, however, what's going to happen is the dipoles within the insulator are all going to line up in such a way that like the positive end of the dipole, like if I were to draw it up here, will be close to the negative side of the plate, and the negative side of the dipole would be close to the positive plate. So they'll kind of line up like this. I'm just going to draw one layer here in my dielectric. Okay, so like inside the dielectric, when it's exposed to that external E naught field from the charged plates, the dipoles line up. And what happens is you get a second field. Okay, and that second field is in the opposite direction. It's from positive to negative inside the material. Okay, and we call this field, I mean, you can call it whatever you want, but we'll call it EI. I don't know why. Just so this is the field. It's the field that is created by the alignment of the dipoles in the insulator. Okay, so let me define that here. It's the field created by the dipoles inside the dielectric material aligning. It like the alignment, the created by the alignment of those dipoles. Okay. So what happens is that the net electric field, so E net, is the sum of them, right? So like the total E net is going to be the original field created by the external plates minus that field that is created by the dipoles. Okay, and what is the case? The case is that E net, I mean, you can see just from this relationship here, E net is always less than E naught, right? Like when you put the dielectric in, the dielectric reduces the field created by the plates. Okay, so it's like you can think of it as like it's a weaker, the net field is a weaker field than the original. Okay. So how does this connect to an increase in capacitance? Okay. So a weaker field, maybe I should add a page here, insert page. Okay, so let me just write it here so that it's not so messy. So we're saying that the E net is the E naught minus the EI. Okay. And the E net is always weaker than the E naught. Okay, so how does this help? Like why does that lead to an increase in capacitance? Well, it basically lowers the potential difference between the two plates. Okay. And remember, well, I mean, why does it do that? We'll just remember that like that potential difference is defined by the electric field between the two plates times the separation between the two plates. Okay, so if this is smaller, then this is smaller. Okay. So a weaker field, let me write it here. A weaker E field means that the potential difference between the plates is smaller. Okay, and that produces a higher capacitance. Because capacitance is just Q divided by delta V. So if delta V is going down, then capacitance has to be going down. Okay, and I think it's important to realize that in this case that I have described here, the charge on the plates is not changing. Okay, there is a case that I'll discuss in a second where the charge, where the charge also changes. It basically depends on whether the capacitor is connected to a battery or not. But in this little sort of thought process that I'm outlining here, we're assuming that it's not connected to a battery. I just slip the dielectric in. The electric field in between the plates effectively goes down, right? That decreases the change in potential between the two plates. And because of this relationship, that decreases the increases the capacitance, right? If I decrease the voltage, it's going to increase the capacitance, right? Because if this goes down, this goes up. Okay. All right. So that's kind of how a dielectric works. Let me walk you through two different cases. And I think like once you see these two cases, it'll become very, very clear. Okay. So in scenario one, we're going to charge the capacitor up with a battery. We're going to then disconnect the battery. And then we're going to insert the dielectric after the battery is disconnected. It's sort of the same situation that I just described. Okay, but I'm going to write out the steps like explicitly. Okay, so let me draw it actually for you. So step one, I connect the capacitor to a battery. Okay, I get a charge. I get charge buildup on the two plates. Okay, so I get like a positive Q on the positive plate and a negative Q on the negative plate. Okay, so that's step one. Charge up the capacitor. Step two, disconnect the battery. Okay, so step two, I'm going to just have the charged capacitor. And the battery is now out of the picture. Okay, disconnect the wire. So now the capacitor is not connected to anything. Step three, I'm going to insert the dielectric. Right, so there's going to be like an internal field pointing in this direction, and the external field is going to be pointing in that direction. Okay, so let's talk about what changes and what stays the same. So the Q on the plates does not change. Okay, between and what I'm like interested in is the difference between picture 2 and picture 3. So like as I go from here to here, like what changes? That's the question I'm asking. Okay, so let's list on the side here what changes. So and what doesn't change. Okay, so Q stays the same. Okay, why is that? It's because if it's no longer connected to a battery, there's nowhere for the Q to go. Okay, so the Q is like it's on the plates. And I mean, eventually it will leak off over time, but I mean, we can ignore that. There's no conduit, there's no wire for the charge to go through. And so between between step 2 and step 3, where we insert the dielectric, the Q stays the same. Okay. The capacitance increases for the reason that I just described, or for the reason that I just explained. Okay, like capacitance goes up by a factor of whatever your dielectric constant is. So you basically take the capacitance that you had before in air. This is whatever the capacitor had before in air, and you just multiply it by the dielectric constant. Dielectric constant. Okay. Let me let me write that better. Sorry. I don't want to use arrows because it'll make it confusing. So this is air, the air capacitance. And this is the dielectric constant. Okay, so the capacitance increases. Why does it increase? For the exact same reason that I explained up here. It's like this logic. The field is weakening. You're weakening the field with the dielectric, and therefore, so this is going down, and so therefore the change in potential between the plates is going down. And if this goes down, capacitance has to go up. Okay. And Q, we can now kind of definitively say in this situation that Q is staying the same. Okay. So the capacitance increases. The voltage decreases, right? The V decreases. Okay, again, because the field is weakening, so the potential difference drops. Okay. I mean, another way to look at it is we know that V is Q over C. So if the capacitance is going up and this is staying the same, then this has to be decreasing. Okay. And then the last thing that we need to sort of like talk about is the energy. So the energy, remember, energy with respect to a capacitor is Q squared over 2C. Well, if the capacitance is going up and this is staying the same, then the potential electric energy is actually decreasing. Okay, so the energy decreases. This is troubling to a lot of people. This is like a confusing point. When you insert the dielectric, it's weird that the overall energy would decrease. The way that I think of it, like you might have the question, like, where does the energy go? Well, you can think of it as like the capacitor is sort of drawing in the dielectric. It's like it's almost like it kind of sucks it in. And the field does work on the dielectric to draw it in, and that decreases the energy, the potential energy of the entire system. Okay, so that, I mean, that's how I think of it. Okay, so now we've listed all of the things. So the Q stays the same, the capacitance increases, the potential difference decreases, and the energy decreases. Okay, this is the situation where you insert the dielectric after the battery has been disconnected. Now let's talk about the other situation, which is I've got like the capacitor and it's connected to a battery, and I insert the dielectric when it's still connected. Okay, so let me just draw that. So I've got my capacitor. Okay, how did it get charged? It got charged with the battery. Okay, so the battery charged it up, right? So I've got positive Q on one plate, negative Q on another plate. And then I insert, so I insert the dielectric while the wires are still attached to the battery. Okay, so the same thing happens, like you get this polarization that takes place inside the dielectric, right? And that creates its own, E field, which opposes the E field, the external E field from the capacitor plates. Okay, but the main difference here is that now the charge is not fixed, right? Because it's connected to the battery. So charge can change because charge has like a conduit, a pathway for it to go. The other major difference is in this situation up here, we said that the voltage changes, it actually decreases. Here, the voltage can't change because the capacitor plates are connected to the battery, right? So if this is a 9-volt battery, then the potential difference between these two plates must be 9 volts no matter what I do to it. So like the potential difference here between these two plates must be 9 volts. Okay, it doesn't, I can insert however many dielectrics I want. It still has to be held at 9 volts, right? Because of the relationship, like remember we said at the beginning when we were talking about circuits and capacitors, once the plates are charged up, this whole path is an equipotential line, including the plate. Like that's an equipotential line that is held at 9 volts, and the other side is an equipotential line held at 0 volts. Okay, so nothing can change that. So in terms of our list of like what's happening here, the voltage stays the same. Okay, and that's going to be like if we call that V naught, it's just going to be V naught. It's going to stay at that same voltage. Okay. The capacitance is going to increase, right? That doesn't change from the first situation. The capacitance increases, and it increases, in the same manner. Like you take the dielectric constant and you multiply it by whatever the capacitance was when you just had air in between the two plates. Okay. Now, however, the charge is going to increase. Okay, why is that? Well, we know that Q is C times V. So this stays the same, right? But this is increasing. Too many arrows. C is increasing. So therefore, Q has to increase. Okay, so the charge increases. So the way to think of it is like when you slip the dielectric in, the battery has to pump more charge into the plates in order for it to maintain the same voltage. That's the way I think of it. It's like it has to hold the voltage at 9 volts. The only way it can do that after the field has gone down is to pump like more charge onto the plates. Okay. And then the last thing to kind of say is the energy. So the energy actually increases in this case. Increases. let's talk about why. There's a couple of different ways that we could look at this. So we know that the potential energy is just Q squared over 2C. Well, I'm increasing the capacitance, right? But I'm also increasing the charge. So like both the top and the bottom are increasing, but the charge is squared. So the top part of the fraction is going to increase a lot more than the bottom part of the fraction, and so therefore the energy is going to go up. Okay, another maybe like cleaner way of looking at it is to look at one of the other formulas for electric potential energy. We can say that electric potential energy is equal to 1/2 CV squared. Voltage is the same. Okay, capacitance increases, so energy has to increase. Okay. So those are sort of like the two scenarios that I think if you keep them straight in your head, you can never go wrong. Like and one of the problems, or maybe two of the problems on the challenge sort of test your understanding of that, of those two different situations. Okay. Okay, so these, I think this is the last thing. So there's just two examples that I wanted to show you. So you've got a 20 picofarad capacitor is charged to 40 volts. The battery is then just disconnected. So this is case A. I put a dielectric of Teflon, which has a dielectric constant of 2.1 in between the plates. And I want to know, like, what is the new voltage of the capacitor? And what is the difference in the amount of energy stored before versus after? Okay. So, okay, so because the battery is disconnected, I always kind of start with the charge, right? So like we know that the charge is going to be equal to the original charge, right? Like there's no change in charge. Okay. And I know that the original charge is just the original capacitance times the original voltage, right? And so that the original capacitance, this is like the original capacitance. This is C naught. Okay. This is V naught. Um, and then I'm looking for like the new voltage and the new energy. Okay. So Q naught is just equal to C naught times V naught. So C naught is 20 picofarads and V naught is just 40 volts. So this is going to be equal to 800 picocoulombs. Okay. Um, I need to know what the new capacitance is. Okay, basically like the new voltage is going to be equal to V the original Q, which is because Q doesn't change, like I can just use that Q for the new Q as well. Like um let me think of a better way to write this. So like this is going to be equal to like, but Q new is the same as Q naught, like because there's no change in the Q. Okay, so actually probably better just to write Q there because it doesn't even change. So it doesn't, so I'm just gonna write that as Q. Okay, and then this is going to be the the new capacitance, right? So the new voltage is, I'm just going to take the Q that doesn't change and divide it by the new capacitance. How do I find the new capacitance? This is kind of, let's call this step 2. I just take the old capacitance and multiply it by kappa. So kappa times the old capacitance. So this is 2.1 is the dielectric constant for Teflon. And then I multiply that by 20 picofarads. Okay, and that gives me 42 picofarads. Okay, so now I know that, and then I can easily calculate V new. It's just going to be this, right? Because that doesn't change. 800 picocoulombs divided by 42 picofarads. Okay, and that should equal approximately 19 volts. Okay. So we should, okay, so that's basically part A. Okay, part B, so I can calculate the old, like the original potential energy, right? So I should have left myself more space here. So the original, like let me call it like U naught is just 1/2 C naught times V naught squared, which if you plug those numbers in, you got 16 nanojoules. And then I can actually calculate, this is kind of a neat shortcut. I can calculate the new potential energy just by taking the original and dividing it by kappa. I mean, you can substitute in the new values for C and the new value for V and like multiply the numbers out. You should get the same answer. But a shortcut is just to take that 16 nanojoules and divide it by kappa. And that gives you like how much the new energy is. And it's reassuring that it went from 16 to 7.6. So, and we said, remember we said in case A up here, the energy decreases, okay, when you insert a dielectric if the plates are not connected. And so that is in fact what happens. It goes from 16 nanojoules to 7.6 nanojoules. Okay, last example. Okay, so here's like the exact same situation, except now the battery remains connected. Okay, so we want to know what is the new voltage of the capacitor. Okay, so the new voltage of the capacitor is the same as the old voltage of the capacitor, right? So like this is a situation where I've got the capacitor and I've got it connected to a battery, right? The capacitor charges up. Okay, the battery is 40 volts. Therefore, the difference between the two plates must be 40 volts always, as long as it's still connected to that battery. And then I insert the dielectric and it's still connected. Okay, so it has to still be 40 volts. Okay, so like in answer to the question A, the voltage is constant. So therefore V equals V naught, which equals 40 volts. Okay, so for part B, we're just asked about the difference in the amount of energy stored before the dielectric is inserted versus after. So to calculate that, so we can say that the new potential energy is just equal to the old potential energy, which we calculated up here. Remember as, or no, sorry, that's the charge. Where is it? Here, right? We said the old potential energy is 16 nanojoules. So 16 nanojoules times kappa will give you the new one. So 16 nanojoules times 2.1 is around 32 nanojoules. Okay, and so the stored potential energy when you insert the dielectric, if the capacitor plates are still connected to the battery, goes up, which is what we reasoned through here, right? The energy increases in case B when you insert the dielectric. Okay, let's just say that for this question we were asked, I mean, we're not in this, there's no question that asks about the charge, the new charge, but let's just say that we were asked to calculate the new Q. When you insert the dielectric, if the plates are still connected to the battery, we know that you can pack more charge on the plates. So the new Q is going to equal the new capacitance times V, which stays the same, right? So the new capacitance is just 42 picofarads, right? We calculated that in case A, times 40 volts, which doesn't change. So that's equal to 1680 picocoulomb, which should make sense because it's about double, right? Like if you look at the original charge on the plates, it was 800 picocoulomb. So this should make sense because you're doubling, the capacitance is going up by a factor of 2 because you've got a kappa of 2.1. Okay, so that's the end of the third video, and that's pretty much all I wanted to show you. You should now have a complete understanding of capacitors, capacitances, and dielectrics.